Hello, today we have a practical lesson on motion with acceleration. Let's start solving problems. A cyclist is finishing repairing a flat tire when his friend, moving at a constant speed of 3.5 meters per second, passes by. 2 seconds later, the cyclist gets on his bike and accelerates at an acceleration of 2.4 meters per second squared until he catches up with his friend. How long after the start of his movement will the cyclist catch up with his friend? How far will he travel in that time? What will be its speed at this point in time? In this problem, we have several questions. Let's write down the conditions of the problem and see how we can solve it. Immediately, we will write down what is necessary to determine in this case. The first question is the travel time of the cyclist. That is, this is the time he will spend starting from his start and until he catches up with his friend. Then it will be necessary to determine the distance he will cover in this time and what speed he will have acquired by the time he meets his friend. Let us also denote this speed by the letter v1. Now, what do we know in this problem? We know that the speed of the second cyclist, it's constant. I'll denote it as v0. And it's 3.5 meters per second. We are aware that the cyclist, after 2 seconds have passed since his friend overtook him, mounted his bicycle and started riding. Let us label this point in time as t0. 2 seconds. And the acceleration of the cyclist now is 2.4 meters per second squared. Squared while he's catching up with his friend. How would one go about solving this type of problem? There are a few different ways we can approach this. For example, we could use a graph to illustrate the situation and depict how the speed of both objects changes over time. Alternatively, we can try to convey the information in a more schematic manner. Let's start by attempting the latter approach. That is to say, when plotted, the graph depicting the relationship between speed and time for a cyclist moving at a consistent speed will have a specific appearance. That is, his speed does not change. For a person who's moving from a place with acceleration, the graph would look like this. Like this. And here we understand that at some point of time their speeds will be the same. That is, the person who will catch up with the cyclist, his friend, he will catch up with him. But let's try to show this problem from a slightly different point of view. That is, let's see how it works from the point of view of the movement of these bodies. Each of them makes its own displacement, and we will show in the figure how this displacement is coordinated with each other. The bodies will move along a coordinate axis, and the cyclist, who is repairing his tire, will be shown on a flag to indicate his location. His friend walks past him, managing to cover a distance s0 in just 2 seconds. He maintains a speed of 3.5 meters per second. Denote this distance as such. And at this moment of time, that is, this friend is moving at his speed v0. The second cyclist starts to move with some acceleration a, and somewhere at this point, let's put a second check mark here, they meet. That is, this cyclist passes his path S, we will look for him with the second question, and here, at this point in time, he already acquires some velocity v1. It will be determined by us as well. The initial velocity of the cyclist at this instant of time is 0. That is, he starts with no initial velocity. What we will now determine in terms of this solution method. Here it is convenient to approach from the point of view of coordinates of bodies, because we understand that if these bodies met at some point in time, that is this position. If the bodies have the same coordinate, we can write the coordinate equation for each and determine when they will meet. Let's set the origin of the coordinates at the location where the cyclist fixed his bike. We'll call it 0. Now, if we introduce a coordinate axis, the y-axis, the equation of motion for the first cyclist, who was moving at a constant speed, would be as follows. The initial coordinate of the first cyclist, denoted as S0, is already determined. Then, the coordinate equation of the first cyclist would be the initial coordinate plus the velocity multiplied by the time of motion up to the time of the encounter. We will consider the velocity of the first cyclist as u0 and substitute it into the equation. Now consider the coordinates of the second cyclist who will catch up with the first one using some acceleration. The second cyclist starts at the 0 point, hence his initial coordinate, and velocity are both 0. This means that the equation of motion for the second cyclist will be determined by the expression squared in half. Therefore, we are only left with this specific term from the general equation of motion. Now, given that these two individuals have encountered one another, the coordinates at this moment in time will be equal. So let's equate this expression. S0 plus V0t equals AT squared. In half. Let's now consider the information we still need to find. We have already established the duration of the second cyclist's movement, which is the time we must determine until they meet. We are aware of the acceleration rate but remain uncertain about the initial distance, which we will refer to as S0. By looking at the diagram, we note that S0 represents the distance traveled by the first cyclist, who moved at a constant velocity over a period of 2 seconds. Hence, we can substitute this into our equation. That is, S0 equals the initial velocity, V0 multiplied by T0, plus the initial velocity, V0 multiplied by T. This can be simplified to A multiplied by T squared divided by 2. So we can make this substitution assuming that the motion of the first cyclist was uniform. So let's substitute here the numerical values of the parameters that we have, and we get some equation. Acceleration is 1/10 4/10 divided by 2. We get 1 whole 2/10 of t squared. Now we carry the v0t to the right side, substitute v0, carry it with a minus sign. And accordingly here we have v0 times t0, 3.5 times 2, we get 7, also with a minus sign. It goes here. We end up with a quadratic equation. Upon solving the given equation, 2 roots are obtained, one negative and the other positive. It is imperative that we select the positive root, hence discarding the negative one. The response is 4.3 of a second, representing the time it took for the second cyclist to reach the first one. This answer pertains to the first query we received. We will now ascertain the distance the second cyclist covered until the encounter with their companion. It is easy to understand why he is able to move without an initial velocity, thanks to a specific acceleration. We have knowledge of the duration of the motion, and furthermore, we possess the equation of motion, which is given by at squared. Cut in half. Now we just need to assign a value to it. Acceleration equals 2.4 meters per second squared. Time squared, let's record it in this manner, and divide by 2. So, well, we've got a value of 22.2. 2/10 of a meter. That's the distance traveled by the second cyclist. Well, here, by the way, both the path and the displacement will be equal because the movement was in one direction. Therefore, the displacement will also be equal to 22 and 2 meters. And the final question is speed. What speed has the second cyclist gained? Here we can solve in different ways, because we already know the displacement traveled by the body. We know the acceleration of the body, the time. So there are different ways. Well, let's choose probably the simplest one. This is the equation of the velocity of this body. The initial velocity of the body is 0, so there is only the product of acceleration and time of motion. So this velocity would be 2.4 of a meter per second. Meters per second squared, and a time of 4.3 of a second. Dimensionally, of course, we get meters per second. So the answer is 10.3 of a meter per second is the velocity of this body. So 1 is the answer, 2 is the answer, and 3 is the answer. We've got it. So this is how you can use the equation of motion to describe the motions of a single body. You can describe the motions of several bodies in the same frame of reference and solve for their joint motions. This is very convenient because in general, when you understand how the coordinates of each body behaves, you can make the necessary system of equations and find the unknown quantities for you. Well, that's all for today. Goodbye.